Well, welcome. I'm Joel Limford. This is Andy Flinders. We're both data scientists at Northrop Grumman. We work specifically in the space sector of Northrop Grumman. Space does lots of stuff, everything from satellite to intercontinental ballistic missile stuff.
James Webb.
So all that fun stuff. We're going to talk specifically about some of the work we're doing to manage some of the natural language processing that we've had to deal with and get into that.
Should I give some background?
Sure, yeah.
Okay, first of all, I had a cold last week and it destroyed my voice, and it's only about 50% back. Normally it's sultry and nice, but I apologize. It's not COVID. I was tested. I feel fine. I just can't talk.
Though I guarantee COVID is here.
Oh, somewhere it's here, but it's
so
not
if
in
you
me.
don't have it, you're going to get it.
Not in me yet, anyway.
But anyway, we're all vaccinated.
Little more background. Joel and I went to undergrad together for physics, like you do, right? And then he went and got a job, and I went to grad school. So I have 2 letters in front of my name, and now he's my boss. So that's how that works out. So do what you got to do.
I did get a master's.
Yeah,
so
well.
It helps, but
he did it while he was working. How the heck do you do that? Whatever. Okay. A little walkthrough here. First, we're going to talk about the kind of text that we're working with on our project. I really think that the technique we're using here will work with almost any text. So think broad, but I'll tell you what we're doing. We're going to be using some BERT embeddings. Show of hands, who knows what BERT is? Okay. Was that everybody? Raise your hand if you don't know what BERT is. Okay. I'll give a brief.
We were going to talk about it either way.
Oh,
so
yeah, because it's part of the talk, so we have to do it. Then we're going to talk about the clustering techniques we're using, and then, yeah, you'll see.
So I have to say I am super excited to be here, and the keynote and the demo they did was super relevant to us. So some of the stuff you see, I'm like already like, let's just get rid of that and change it based on what Graph's doing. But we'll still show you kind of what we've done. But you might ask, what problem have we been trying to solve? And so Northrop maintains and builds weapon systems, satellite systems, things. And those are traditionally, they all have a hierarchy. They all kind of come together. But we're going to talk, which is a graph, and we use that to model how the systems are related. But specifically, we're going to talk about how those systems are maintained over the long term. And Northrop maintains contracts for legacy systems. So things like, F-16s, ICBMs that are developed in the 60s, they don't have convenient, barcoded systems. So they've got maintainers going out and saying, okay, the system's broke, how do I fix it? And they do some maintenance, they fix the problem, and then they go back and log what they did. And when I first started at Northrop, I was on a team that their whole job was reading through narratives that maintainers wrote and trying to identify like if things were a failure, if they were a replacement or whatnot. It was a nightmare. And so we did a lot of work to automate a lot of that. But my point is that what the maintainers are writing in these free-form fields is the majority of the information that we get. So they do have like action taken code saying like, oh, okay, I took something out, but then they talk about why they did that in the narratives. So show of hands, who here has dealt with free-form text in some form and enjoyed it? See, all the hands went down. Okay, sorry, good point. So you're the odd man out, obviously. If we had a graph, you'd be off on this side. Yeah. But it is a hard problem, is my point, is that we as humans interact with text, or we think in language, but we don't, until recently, there hasn't been a very convenient way to embed that. So we'll go over that a little bit more. But you might ask, okay, well, all this information is in the narratives. What do you even want to do with that? So our end goal is to say, okay, given all the information we get in, let's talk about what we expect the system to continue to do. So we build a digital twin, we build predictive analytics to say, how's the system going to perform? What supply chain draw is going to be needed? Mostly we're trying to say, if you want to maintain like 99% uptime or whatever the Pentagon wants to maintain on this weapon system, these are the actions you're going to need to take. That all trickles down to budget and whatnot. So, okay, back to text. We basically were thinking, okay, let's combine, let's try an ensemble approach and just do all of the natural language methods. So we use BERT, we use clustering, we use graph algorithms, and we've found some interesting results.
That's why we named it fusion learning, because, we'll get to it, but basically it's using deep learning, shallow learning, and graphs together. Okay, so these are some examples of the narratives that we're working with. I have changed the nouns, like the objects, to be car parts for your protection. But other than that, these are real narratives. So you can see how descriptive they are, whether or not this would get you very far if you were expected to read one of these and understand what was going on when the maintainers went to repair the system. Okay. So, BERT. I'm going to use a BERT as an example here, but there's a lot of large language models that do the same thing, basically, like GPT-3, Alberta, there's a bunch of them. But I'm just going to use BERT because I found their paper and referenced it, so I'll just use BERT as a representation of all language models for now, or transformer-type language models at least. Basically, what BERT does is you give it text, and it's a very, very large deep neural network that has been trained, in this case, by Google on something like all English text ever written, or something close to that. With a couple of specific exclusions, like it was not trained on Twitter or Reddit purposely. So,
and that's because they wanted English. They wanted something that understood English, which,
So that's probably legitimate. But basically, transfer learning is very helpful for us because while we're working with these narratives, we don't have enough of them to train our own language model. So if we want to take advantage of these, very powerful transformer-type neural nets, our only option is transfer learning. And fortunately, they're very successful at that. So basically, this is an image from the original BERT paper, which is called "Attention is All You Need." If you don't know about BERT, this is where you should start, is reading this paper. But one of the things that makes these transformer-type neural nets so powerful is they create these attention vectors between the words of the sentences. So this sentence is, "The law will never be perfect, but its application should be just blah, 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 blah." Okay? And these green lines represent, in BERT's opinion, how related each word is to every other word in the sentence. And you can look at the strength of the bars and decide whether or not you think it's doing a good job. You can actually produce these plots on the fly for your text. I've never done it, but you can. And then you can decide whether or not it's picking out what you think are good relationships. But this is one of the reasons why these language models have been so successful at dealing with natural language. Is this is how people think when we read English, right, or whatever language you're speaking. We notice that like "the" is referring to law, right, and the law will never be perfect. So like we make these relationships in our heads how we think about language, and the fact that we now have neural nets doing this in such a flexible way is what has made, BERT has changed basically all natural language applications now use transformers. And if you are working with natural language and you're not using a transformer, you're most likely wrong, unless you already know about it and know why you're not using it. So anyway, that's some background on BERT. But basically, for the purpose of this talk, what you need to know is you take some text, you put it through BERT. This is some cipher note, right? Okay, and you get a big fat vector. Okay, and this is 500 character long, or 500 entries. What do they call them?
Yeah, so components or vector space.
Yeah, components, and those numbers in this vector represent the meaning of the text. Yeah.
So after we get those out, and this is where I'm kind of diverging based on what we saw this morning, but when we were doing this research, we didn't have the graph algorithms built into Neo4j, but I want to do that now. So you can think about those vectors of a sentence. So we take the text, we put it in a vector, so now we can talk, a computer can interpret it. And so what our goal is we say, okay, people are talking about things, and we want to classify what they're talking about at different kind of states or magnitudes. So like this morning in the talk, they were talking about, he showed the picture of the guy who did the Republican or Democratic classification. So let's take that example. If you think about like tweets, for example, you could say, all right, like if I'm going to try and predict some political bias or landscape, I can say, all right, there's probably two groups that at the large scale, there's like a right wing and a left wing. And then so you could cluster those, and then you can start clustering at lower levels, and you might identify topics that both of those groups discuss, and they're polarized across. So the same kind of idea goes here, is we want to identify the topics or the, like, I don't know,
broad stroke
ideas of these narratives, so that we can start to make predictions on what's going on, and specifically classifying, are these things broken? Are they being repaired? Those are kind of mainly what we're interested in. So if you think about, we've got these big vectors, 500 characters, and so that's a big vector space to explore. The thing about clustering is there are some algorithms that are good at one thing and not good at another thing. So let's contrast like optics and like k-nearest neighbor. K-nearest neighbor assumes you've got a sphere basically in your high dimensional space and says, okay, I'm gonna like go add this item to that sphere of that cluster. Optics is good at like identifying kind of banana-shaped clusters. So you can think of like two bananas that are intertwined. A spherical clustering algorithm would be really bad at identifying those two groups. Optics will basically, like, if you think about a little guy running in a bowl, he's gonna like try to run along the least gradient. That's what optics does, is it says, okay, if I'm gonna run in a direction, I'm gonna go wherever the least delta is. So optics will classify like bananas.
Yeah.
Banana bugs.
Kind of does like almost like a crystal growth.
Yeah.
Path of least resistance, agglomeration of clusters. It's pretty cool. You can look at the details. It's very similar to DB-scan if you've heard of that. But one of the things that we like about the optics clustering algorithm is it doesn't force everything to be in a cluster. I know these images are probably not very clear for you, but there's a bunch of gray points that were sort of like loosely grouped around here that it does not put into a cluster, as opposed to KNN, which you tell KNN make 10 clusters and everything goes in one of those clusters. Yeah. So sometimes we found both to be useful in different situations. Sometimes KNN, if you say make me 20 groups, it'll find like types of repairs, like scheduled maintenance will be a group on all kinds of different parts, or corrosion control on all kinds of different parts. But optics might be really good at picking out, oh, these are all pump repairs, these are all shock isolator repairs, or whatever.
Bearing repairs or whatever.
Yeah, whatever it is. So they're useful. They're good at different things.
Our point is that clustering algorithms make assumptions, and those assumptions are different depending on how the clustering's built, and some are convenient in different ways.
Yep. Okay, these are some real clusters. Actual narratives, again, with the objects, or the nouns changed for your safety. But these are real entries. And these are optics clusters. They tend to be a little bit smaller and tighter because they'll just leave something out if they don't like it. So some of these, to me, are very impressive. I'll go to the next slide here, where it will start to, in a way that I find completely mind-boggling, it will start to find synonyms or abbreviations. Like this one says, perform CC, which when the maintainers enter CC, they mean corrosion control. And I know that because I've read 1,000 of these. But I don't know how optics knows that. or really it's BERT that's encoding the meaning of these two, and it's encoding them so close together that when optics runs its clustering algorithm, it's recognizing them as meaning essentially the same thing, and so they get thrown into the same grouping. So anyway, so this is, like I said, this is an example of an optics clustering, but we run this and also KNN currently. You want this?
Oh, yeah, sure. Well, you go ahead.
Oh, yeah. Oh, these are some examples of entries that aren't clustered. These are not real ones. I made these up. But I could have found real examples if I wanted to. This would be like, sometimes they'll enter text into the wrong field, like, and they'll end up putting a serial number or something, and you're like, okay, well, that's not helpful. Or maybe you'll want to put it in the correct column, so then that entry becomes useful. Sometimes it's like typos. And so BERT is like, what the crap is that? And it ends up off in who knows where. Sometimes they're just extremely short and not that helpful descriptions. So you get those. But sometimes you get really, really unique situations where they were doing a repair that really isn't like any others. So what I spent a couple of days looking through some of these, like last year sometime. And if you sort through the kind of the nonsense that doesn't get clustered, you can find some really unique situations. So that may be interesting depending on what you're trying to do. Go ahead, Joel.
So, okay, we talked about, we take text, we embed it with BERT, we cluster it, and then, okay, what do we do then? So part of why we like this approach is normally when you're doing a traditional clustering algorithm, all that kind of happens in memory. And you say, okay, like I'll try these things, oh, that didn't work, I'll try these things, make some plots, all right, okay, kind of figure out this is kind of the clusters of my space that I'm exploring, and those are convenient for whatever reason. So what we're doing is in each one of these red nodes is a narrative. So that's got the text that the maintainers entered that's embedded, and then we cluster that and we import that into Neo4j as the nodes and the cluster centers. So basically saying, well, not a cluster center, but a cluster identifier node. And we can put whatever we want on that cluster identifier. So for example, if in KNN, it makes sense to say, okay, let's use like the cluster center. And so we can average all of those embeddings and say, okay, this is like where that cluster center is located within that cluster. And then you can start to take deltas between those cluster centers and the nodes inside of them and start to say, okay, like how tightly clustered are these things? And that's convenient because as you're running this, you can identify different layers of clustering. So let's go back to like the political example. There's two groups, but then there's topics within those two groups. And so you can say, depending on how fine you make your cluster segmentation, you might be able to identify, okay, these are two groups, and these are the large clusters if I have two clusters, but then as I continue to cluster, I break those into smaller groups. And by saving that into the graph, we now maintain state and can explore that space at a later date. So one convenient thing about this is that you can start to say, okay, like how similar are these clusters in space related to each other? So now you're not saying, okay, what are these narratives, like grouping them together, but you're starting to say, okay, like how polarized are these groupings? One thing I want to try is to start to do this with the graph algorithms that were shown this morning. So we can say, like, instead of making a single node for a narrative, we can break that node into multiple, like whatever 500 embeddings for the BERT model. And then those graph algorithms will actually be able to identify clusterings. So that's kind of the next steps, is we want to start doing that kind of stuff. So back to our end goal of saying, how do we identify centrality? How do we identify like what are the key underlying broad strokes? So then we can start querying our graph and say, okay, what, for this aircraft, are they experiencing corrosion increase over time? Like, or you can start to say, like, let's identify which aircraft have gone through flight and storms and whatever, or stored in humidity, and you can start to identify and link all of those things together.
So I kind of mentioned this before, but one of the things that I really like about what we're doing here, and we've made some of these changes, whatever your text is, like you can pick and choose the language model that seems to capture the context and connotation of what you're doing freely, right? All you need is the embeddings. So I mean, you can make a fine-tune model. That's something we've looked. In fact, I think we have a slide about that next. You can fine-tune a model to learn the particular jargon or abbreviations or whatever that you're dealing with. But you can switch them out, or a new language model comes out. I mean, I swear Google puts out a new language model every month, and we're like, well, crap, we should use that one, right? It's way better. So you can just swap it out. It doesn't matter. Once you get your embeddings, you can use whatever clustering algorithm you want. Maybe optics doesn't work well in your application. That's fine. Use any of them. All the ones we've tried, excuse me, were from scikit-learn, but there's all kinds of advanced clustering algorithms. Heck, I don't know. There's probably clustering algorithms that are designed to work with BERT embeddings, and I haven't even found out about those yet. But you know, pick your clustering algorithm, it doesn't matter, but then take the outputs of those and put them into the graph. And there's 1,000 ways you can structure that graph and adjust it. So it's sort of a plug and play approach to using this transfer learning, this shallow learning, and these graph building techniques to illustrate large scale, broad stroke patterns in the text that you're working with. So we found some success with this, but we're still, it's an ongoing experiment. We're still trying different things.
So, yeah, do you want to take this one?
Oh, yeah. We do have one. So I have looked into fine-tuning BERT, and if you don't know what that means, so BERT is basically trained by ingesting lots and lots and lots of text, and through that process it learns English. So to fine-tune it, you just let it ingest the text that you're working with, and it will pick up the kind of new vocabulary. I mean, this is basically what you do when you get a new job, right? Is you already know English. Well, now you sit down and learn the vocabulary that's necessary for your new job, right? There's some new phrases or some new ways of speaking that you're not used to. So BERT picks up on those. And this actually happens pretty fast. So even if you don't have a ton of training data, like to build your own model, even with a couple thousand or 100,000 examples of your specific text, you can fine-tune the model to kind of pick up on those, on that jargon. So we do have this working. I haven't fine-tuned it to a degree where we've swapped it into our pipeline yet, but we're headed in that direction. And I would guess that you're probably gonna have to do this no matter what you're doing. Like I said before, BERT is purposely not trained on Twitter, so if you wanted to do Joel's example earlier, you're gonna have to fine-tune on some tweets so it can learn what ROFL means or whatever, right? Because it doesn't know common parlance in the modern day.
Or emojis, like you can train on emoji. Like it would,
as long as it will encode them, I don't know.
Yeah. I mean, it will encode because it's got a text format. So
there you go. You're right.
But this is particularly useful for us because I don't know if any of you have worked in the DoD space, but it is like when you start, it is like hitting a wall of acronyms. You're like,
it's insane.
6 months, you're like, I have no clue what anybody's talking about. So we are definitely doing this, but with any kind of machine learning, we try to find that baseline. So we say, okay, let's start with BERT as is, and then we'll baseline that, and then it's going to take work to train it, and we can quantify our.
Joel was yelling at me just the other day that I need to actually like set up a set of parameters that we can compare a generic BERT with a fine-tuned BERT to say, oh, it's 20% better at whatever. Anyway, I haven't done it because I'm here, but I'm getting there.
So some of the thing we wanted to talk about specifically, we noticed so you got these cluster identifier nodes, and if you want to start to say, okay, like this cluster is like summarized by these embeddings or whatnot, as you average those embeddings, or you could take different summary statistics. But one thing we're running into is that vector space is so large that if you try and condense it down to a single few summary statistics, you start to lose semantic meaning very quickly. And so this is something we're playing around with right now, is if you are identifying the types of clustering algorithms you want to do, you're going to want to tailor what you're storing in your graph depending on those. So like our example, optics and k-nearest neighbor, you don't want to do the same type of embeddings for both of those things. You would just confuse yourself because the average, point of a banana isn't in the banana. It doesn't make sense to calculate stuff like that. So we're looking into this. I am interested in all what the specific graph algorithms they have in the data science libraries they've been announcing with the APIs. So that's kind of our next step is say, let's break this out and start to explore using Neo4j's native clustering algorithms and then compare and contrast those to what we're doing.
We came across this when we would say like, all right, well, the average of this cluster, what's the closest cluster to it? And sometimes that second cluster would be very similar to the first, but sometimes it makes no sense at all. So I think just breaking these 500-degree vectors down to like the distance, a single scalar distance from here to there, you just lose too much.
Yep.
And it's not reliable.
So do you want to take this one or do you want me to?
I can't remember. Go ahead.
I'll do it. So just to kind of loop back to our end goal is that by doing this segmented training and like shallow learning at different depths and storing all of that information, our hope, and we've kind of seen this, is we can start to identify these ideas that people are talking about. And so you don't need to like read 500 narratives to say, okay, people are now talking about like COVID, like for example, like if you're doing tweets, that type of information would pop up as a new cluster over time so that you can identify those. But for our system, if you are talking about, we've got the red nodes are identifying like different types of systems. So you've got a car, you've got an engine and a transmission, but you can identify there's scheduled maintenance that needs to occur on both of those things. So the maintainers are entering information and working on different parts of the system, but they're doing the same type of thing. And we can start to use that type of information to predict what's going to happen next.
Right. So this would be sort of what you might find if you did first 2-group KNN clustering and then a 5-group KNN clustering and then link them together. Of course, we do much more than that, but you can only fit so much on the slide. So there's our references. So you should read all these stinking papers, and because I know you've got time for that kind of stuff.
You're going to be on a plane, so you know.
But we'll take questions. So thank you, guys.
Right in the back.
Thank you, first of all. It's a great talk. I was wondering if you guys have experimented with, because I know you guys are trying to sort of cluster chunks of text, but what about if your text is of variable length? Let's say you're trying to cluster documents. Some of them can be like a few sentences, some of them can be thousands of pages.
So BERT in particular will take up to 512 tokens, which is almost equivalent to words, but not exactly. Some words are broken into 2 or 3 tokens. But let's just say like up to 400 words, BERT will just take it and output vectors of the same length. So that's very convenient. But once you pass that limit where your text is too long to fit into BERT in a single piece, then you're going to have to be creative. So I've seen, go ahead.
What I would say is this is kind of to the point of how you can make this with graph is you could stream a long document through BERT and say, okay, I'm going to have a window that streams through that document and embed it into different tokens. You have a document, you've got the token nodes, all of these are contained, these are followed in a sequential sequence. So then you're starting to say, okay, like I'm going to capture what these blocks of text are meaning in a given document, and I'm storing the state as it gets streamed into the graph, and you can start to explore that.
Yeah. So maybe paragraphs or some kind of sliding window, embed each piece at a time and link those in the graph. Yep.
Have you ever run into the problem where BERT gives you a lot of clusters, like above 100 clusters or something?
Yeah. So when I was playing around with the KNN, I actually I set it up to loop and run KNN with one group, and I went up to 500. And it definitely started to lose meaning to split them at a certain point. With the data set I was working with, that seemed to be around 200. Like past 200 clusters, it was like, well, these two are literally identical. Like you shouldn't have split that. So you just have to test it. Like KNN is nice because you can set the number of clusters, right? You just tell it how many to make. So play around with that, and I sort of used that to guide the number of clusters I was looking to find in some of the other clustering algorithms. So I would say that, find one you can tune, find something that seems to be working, when you look at examples, and then carry that idea with you into some of the more unsupervised clustering techniques like optics or dbScan.
I want to unpack your question a little bit. So did I hear you correctly? You said where BERT is giving us the multiple clusters? Is that what you asked?
Yeah.
Okay, because BERT doesn't cluster, it embeds. So it takes text and transforms it into a vector space. And then we're running a KNN or a clustering algorithm on that vector space So that's what Andy's saying, is you can tailor that clustering algorithm on the vector space, but that's kind of independent of BERT. BERT's just it's a transformer to say, we take the text and embed it into vectors. Yeah.
Right, right.
There was another question, sorry. Yeah, go ahead.
I was just curious. Your use case seems very similar. So in the past, like that you worked at an insurance company, and it's very similar, like very low context text, where lots of acronyms about V1 H V2, like V1 hits V2, that sort of thing. So it's like gobbledygook.
Right.
And so I was wondering, once you had the vector space generated from BERT, because you mentioned that you, like for KNN, you just like ran a loop for, one cluster up to 500. And so did you use any kind of like optimization, like given that there are these distances between centroids or anything like this, that you can actually look at, I don't know, like the elbow method or something, something like that. Right?
Yeah, I plotted out the elbow curve for when I ran that loop. Yeah, and so it's pretty clear, like when it dips out, like, well, these are doing nothing, So I would just say try it, like just see where you're at. If you run it through a loop like that and you get up to 500 and it hasn't like kinked, I don't know, maybe you need more, right? There's other things you can do. I mean, there's sort of like traditional NLP techniques you can use. Like if you know that V1 always means vehicle 1, like just switch it before you give it to BERT, right? Like you can do your text cleaning all up front and get it into the best state that you can, then pass it to BERT, if that helps. Yeah. And you can compare before and after. Do your text cleaning and don't do your text cleaning and see if the clusters make more or less sense. Try it.
Because otherwise I was just going to suggest, because I was really interested and happy to see that more people are using DB scan on a regular basis. But one thing that might be worth trying is using hierarchical clustering methods instead. So like
yeah,
scan,
I have not tried that.
That tends to work really. This is like my insurance, so I don't know. Maybe it'll work similar to your data.
Yeah.
It's as bad as the insurance things are. Then the hierarchical method might. I don't know. Maybe it'll be better. Maybe not.
So were you using language model embeddings and clustering on those? Oh, cool. So you're right up our alley.
And like also did try to play around with dimensionality reduction, like on the vector space.
Yeah. We were just talking about that.
When you have like 500
right.
elements to your vector list, then that can sometimes, it's just like using, you might as well just throw in the raw text and hope that something happens.
Yeah.
Right.
Like as soon as the dimensionality is so high, then it gets really difficult.
So did you have success with the dimensionality reduction?
I mixed.
Man, you got to get up here and give this talk. What are you doing?
Sometimes, but other times, and like I found that it worked for some lines of business and not others because the language was different.
Yeah.
It had more acronyms than others.
Yeah, that's definitely something we found. Is like this seems to work really well for some things and sort of mediocre for others. But I think with like adjustment and changing models and clustering, I think you could probably find something that would fit most things.
Yeah, and I really like using the graph to store that state because it's hard to keep that in your head as you're starting, like as a data scientist, you're like, okay, like, I don't know, I feel like an ADHD kid all the time. I'm like, well, I'll try this. Oh, I'll try that thing. And then I'm like, well, what did I do back there? But if you're storing the state of that information and those experiments in your graph, then you can start to say, okay, like these are the clustering and the groupings where the embeddings helped or I can do this is where cosine similarity worked and this is where Euclidean distance worked. And so you can start to see those things come out and because you're storing the state.
It's a very creative use case. Did you look into some business outcomes through this application? For example, you're doing schedule maintenance on parts or subsystems, and that schedule was changed because you learned something new. That when you're looking at this part maintenance, you ought to consider these as well, or how these things are impacting readiness of subsystems and therefore the system. Did you go there as well?
We haven't really made it to that point yet. I would say I've been sort of working on this for like a year and a half, but very off and on. So even though it's been a while, I would say we're very early in research stages. Like we haven't even made up our mind of exactly what clustering techniques we like best or whatever. But that's where we want to go, right? What's for dang sure is the text does have important information that our stakeholders want to know about. So it's just a matter of like bridging that gap, like exactly what technique will get us there. But that's what I like about this technique is it's so like plug and play. Like there's some combination that's going to get us there, and we just haven't found the perfect one yet.
Well, and then it's really nice to be able to have that, I'll get buzzwordy here, but you have that digital thread in your analysis all the way back, so it's explainable when you say, okay, I'm going to say, as opposed to me going to our leadership and saying, all right, here's my Jupyter notebook you don't care about. Then you can start to say, okay, like, this is the path, like this is my logic in my graph because I stored those experiments all along the way, and you can show that and kind of explain it as you brief, or at least you have that data store to explore. What was the other question?
Well, actually, just before I ask the question, to add on to the dimensionality reduction, I've had some luck in the past with autoencoders. But my question is about fine-tuning BERT models.
Yep.
I don't know how far along you guys got with that, but the question is, how do you really evaluate if your fine-tuned model has worked? Do you guys run it through the clustering methods?
Right. So that's I've been thinking about that a little bit. The best idea I've come up with so far, and you might hate this, but this is what I got so far. I think what I'm going to do is I'm going to take our narratives, count the words, and take the list, the top 100 words that aren't stop words. So, remove those. I'm going to take those top 100 words and ask the language model to generate synonyms, and then audit those either personally or have one of our maintainers look at it and say, like, out of these 100, how many of these synonyms make sense? So at first, a lot of those words are going to be abbreviations or jargon, right? Because they use them a lot. And I haven't done this yet, but presumably a plain BERT won't know what they mean, right? But we should be able to observe that score increasing once we fine tune on our text. That's my idea. But
when you fine-tune, you train the BERT model on like sentence similarity type of?
yeah, so it's both. BERT's really trained in two ways, and you should read the paper. But so it does word masking. So it'll take a sentence and mask one or several words, and then ask the model to predict what words fill these blanks. And then the other thing it's trained on is next sentence prediction. So it'll take a paragraph and predict, given this sentence, is it sentence A or sentence B that comes next? So between those two, that's how it learns to pay attention both across sentences and within sentences, which is why it can take in, like, say, a whole paragraph, and it does, the self-attention throughout the whole thing. So when you fine-tune it, all you do is give it more text, and you have to do a little bit of work to prepare that text for training, like go in and mask words. And yeah, no, it does not have to be labeled. It's unsupervised. So you automatically mask 20% of your words or whatever. And then you also take paragraphs and set up the next sentence prediction models. And then you just run it through. It's all unsupervised.
So one thing I'm interested in doing is, because in our graphs, we don't just have the text. So we've also got like a system hierarchy and saying like these systems are comprised of these other systems, and those have descriptions, they have categories. And these texts are like correlate or linked to those. They're saying I worked on this part. So now one thing I want to do is say, okay, let's take those connections we've got in the graph and pull them out and say, okay, like maybe they've got, I don't know, like you've got a wheel, it's got a part number. You can say, okay, this part number means that wheel. So if they're referencing that part number in their narrative, they're talking about a wheel. And you could theoretically pull out those semantic, like, closeness or at least traversals in your graph and say, okay, like, let's pull out the narratives and let's pull out the descriptions of the parts and then have those things be related in some way and try and train BERT to say, okay, this thing means that thing.
Yeah.
Wonder, what's the size of the data you're working with? And in this process, you're running to, like, maybe some process takes a long time to run?
Sometimes, yeah. How many narratives do we have? Like 1.2 million or something total?
Yeah, something. Millions on the orders of millions.
My experiments here were a subset of that data, like 20,000, I want to say, lines, I think. I was looking at a particular system, so like, let's just say the transmission. And so I was only looking at transmission repairs while I was doing this, but we have a couple million total.
And I think one of the the BERT embeddings are fast because you don't need to train, like the slow part is this unsupervised, like shallow learning. Okay, let's do, because it's a big space to explore. Like let's do a bunch of clusters over a big space, and we've got lots of clustering algorithms. So that's the problem, is you're exploring a big space. But if you say, okay, like let's segment it and down to the subset our population and randomly sample, pull that in, and you'd identify these groups, then you can embed all of the narratives and say, like, okay, how close are these things to these clusters that we've already identified? So that's a good way to say, let's randomly sample, figure out what people are talking about, and then we can classify what everybody's talking about.
It's still not too bad, though. I can run, like, my pipeline that generates the graph that we have screenshots of here is maybe 10 minutes. So even
and that's on a local machine.
Yeah,
like,
on this laptop. Like, if you expanded that to even our whole data set, it'd be maybe like an hour. Yeah. So it is very slow fine-tuning BERT. That's the reason I haven't actually built a fine-tuned model yet. That takes a stinking long time. So we have some more powerful servers and stuff that I'm going to use. So we're getting there. Okay, sorry, we've been here forever. Like, you guys are missing other talks. Okay. We're not that interesting. But thank you, guys. Appreciate your questions and your time and attention. Appreciate it.
Thank you very much.